we come to statistical decision theory, which asks and answers some very fundamental questions. Yeah? The first question is, what does the very best conceivable classifier look like? And we will give an answer to that, and this is going to be the base classifier, and we will ask, how good is this very best classifier? Best does not necessarily mean good. Yeah, it depends on your training data, on the nature of the underlying distribution. Yeah? And so what we have for statistical decision theory are a few ingredients. The first ingredient is we need a statistical model for the distribution of the data. So joint distribution of features and labels. And secondly, we, the user, the designer, we need to specify in a quantitative fashion, what do we mean by good and bad decision? Yeah. So we need to specify a loss function which takes as inputs on the one hand the true label, and on the other hand some predicted label. And this loss function, it can have many different forms, and earlier we were discussing possible dilemmata and what it means for what the loss function should look like. But the very simplest one, and the one that you used implicitly when you gave answers earlier, was just the 0-1 loss function. Yeah, so if the true label is 1 and we predict 1, then the loss incurred is 0. And if the true label is 1 and the prediction is class 2, then the loss incurred is 1. All right. And now we can have more classes. We can have more than 2 classes. We may also have a class, a special class, where we say, I don't know. I'm calling it doubt here. But if the doubt is more expensive than the worst mistake, it's never going to be used. So how many classes we have and so on depends on the problem, but very often in machine learning, when learning about these algorithms, we often only consider 2 classes, and this would be here. It has a name. It's the 0-1 loss matrix. And this is just the simplest one, and many other choices are possible. And then what we need, thirdly, is an expression for the expected loss. And the expected loss in this field is called the risk, and the risk R of some prediction F. And now, last time and in my correction earlier this morning, I wrote that the true label is f of x plus epsilon. This time, and this is also in keeping with the literature in this field, f has a different meaning. Yeah? This time, f is our predictor. Oh, a prediction f. And so this risk is defined as the expectation with respect to what features are we going to see, what labels are we going to see. And now x and y are not matrices. Here I'm using capital letters because random variables are often denoted by capital letters. Okay, the expected loss here. Okay, and now the task will be to minimize this risk and to find the minimizer. And this risk I can rewrite. I could either write the expectation of y given x and the expectation of x. Here I'm doing it the other way around. I'm writing expectation with respect to x and then of y given x. Of the very same thing. And x is assumed to live on the interval scale. So we can use the definition of what does it mean to take the expectation with respect to x. It is to take that times p of x dx, where this can now be multivariate, yeah, depending on how many dimensions our features have. And now if we want to minimize this, so if we want to minimize the entire risk with respect to f, then this integral can be minimized pointwise. Yeah, we can take this kernel, we can take what's inside this expectation value and minimize that. And so I'm writing this term here separately. Yeah. The question was, can we always switch the expectations? And at this point, yes. Yeah. So if it's a continuous random variable, it is just a question of what do I, it's two nested integrals, and it's the question of what do I integrate over first. The question was, do we need to say they're independent? For this, no. So this is, I just have two nested integrals and I can decide, do I want to write dx dy or dy dx? This is fine. Hold on. I think my integral argument does not work, because what I was just saying is I have an integral of dx, and then I cannot meaningfully say that afterwards I want an integral of dy at some location x. That does not work. Yeah. So so my integral argument does not work. But let me write this expression, and then I think we see that this will be fine. Yeah. So I'm writing here again the loss of y, which is still a random variable at y given y, and my prediction is now fixed to some specific value x, and so in terms of the integration order, this would be fine. Yeah, this would work. Okay, and so now this particular term here, y this time is nominal. So I'm using again the definition of how is an expectation value computed when the random variable is nominal. And this is a summation over all the values that this random variable can take of the loss. And now we can write this for the very special case of this 0, 1 matrix here. Yeah, so next equality is only for this 0, 1 matrix. I can, for whatever prediction I make, I can now sum over all classes except the one that I'm predicting. And if the true label is different from the one that I'm predicting, then my loss is going to be 1. Yeah, so it's this one here. Plus, if my true label is just what I predict, then the loss is going to be 0 times the probability of me making times the probability of my prediction being true at location x. Okay, and now I need to switch boards here, unfortunately. And now we can remember that these are normalized. So if I take the sum over all y of p of y given x, that this is 1, then if I summed over all y, this would be 1. But what I'm lacking is this contribution here. Yeah? So what I find then is that this expectation of y given x is 1 minus the part that's missing here in the summation. 1 minus p of f of x given x. Okay, and we wanted originally to minimize this entire risk. So we want to still minimize this here. And this becomes minimal when this term becomes large. So to minimize the risk, what we need to do is maximize P of f of x at some location x. So in other words, what we want to do is we should, to minimize the risk, we should always predict the class with the largest posterior probability. Okay, and this thing is then called the Bayes classifier. So the very best possible classifier in the sense of minimizing the expected risk. The best possible classifier in the whole world is called the Bayes classifier. And it is given by this class which has the largest posterior probability. Yeah, so f x Bayes is that class Y which has the largest posterior probability. The Bayes classifier here for the 0-1 loss. For other losses, I need to take into account how bad it is to make one decision versus the other. Yeah, but for the 0-1 loss, this is the Bayes classifier. So this was the answer for the first question. What does the best classifier look like? Check. It's the Bayes classifier. And the second question was, how good is it? And well, how good is it? This is then given by the value of this risk. So its risk is given by the smallest value that we can achieve here. And this, unfortunately, well, it could be 0 under very favorable circumstances, but in general it is not. So in general, this risk is larger than 0, and how much larger it is depends on the distribution of my classes. So let me give 2 examples. Let's say I have some probability of x given y1, and I have some other class this time I'm including the normalization factors here, P of y1, and this here is the probability of x given y2 times P of y2. And I need to include it because this one, has a smaller integral than that one. So compare this to, I'm trying to use the same distributions here. but I'm letting them overlap a lot more. So these are two hypothetical scenarios. And the question is always, what's the expected loss? So what is the chance of picking not the label that we predict, but a different label if we sample data randomly? And I asked earlier, when would you rather not make a decision? And one of the answers was, a correct answer, when the posterior is very close to the threshold, to the decision threshold. Because then we're going to make many errors. And okay, in a standard classification setting, you always force the machine to make a decision, even if it's not confident. But its expected error is going to be much larger here than there. Yeah, so if we take, so here we can find a Bayes classifier, and there we can find a Bayes classifier, and this one will have a Bayes risk, and that one will have a Bayes risk. But in the second case, the risk here is going to be much larger than in the first case. And so basically, how big is this Bayes risk? If I take the 0-1 loss, and if my distributions are correctly, so let's say if they have equal prior probability, and so let's say let's pretend that the integral of the green curve here is the same as the integral of the red curve, then my Bayes risk is going to be given by, this chance of getting a different label from the one that we predict. So the bigger the overlap between the classes, the bigger the risk of even the very best classifier. I'll try and show a 2D picture. All right, so what do we have here? Here is a example I created artificially, so I know all the ingredients, and I have here created some, so two-dimensional feature space, and this would be the density of class 1 across feature space. This would be the density of class 2 across feature space. And if you look at the color bar here, this takes much higher values, which has to do exactly with this normalization question that Peter just pointed out earlier. So this thing integrates to 1, and that thing integrates to 1. But now we multiply it with some prior, and the prior in this case, I believe, was 1/3 versus 2/3. So here it looks the same, but the color bar has changed. All right, and now from these I can compute various things. For Bayes' theorem, I can compute the denominator. So this picture I get by adding this one plus that one. Yeah, these two together. So this one and that one, if I add them up, give me this picture here. That's the total probability density. It is the probability of finding a sample anywhere in feature space, regardless of what class it belongs to. But we can also use Bayes' theorem and compute the posteriors of the one class or the other. And here you see, well, where class 2 is concentrated, its posterior is high, and elsewhere, class 1 wins. That's both in areas where class 1 is concentrated and also in these areas where both classes have a very small density. Yeah, so here both classes are, have vanishing probability, but still one of them has a much larger posterior probability. Yeah, so that's the kind of area where we would really not be sure that we can make a confident prediction. Shown in green is the decision threshold. Yeah, so for a 0-1 loss matrix, I can now truncate this plot here at 0.5. Yeah, so I can ask where is the set of pixels that have this particular color, and the answer is, well, the set of pixels looks something like so, and this set of pixels is here shown in green, and this is the decision boundary for the Bayes classifier. So here, the green thing would be, I should probably pick a different pin. The green thing here would be the Bayes classifier decision boundary. So inside, I predict class 2, and outside, I predict class 1. Here, I have sample data from this underlying distribution. And probably if we had only had this sample here, we would not have been able to guess that that my Bayes classifier here has this small nx. If I draw infinitely many samples, then yes, I will be able to see that actually that there are many blue crosses here. But from this small sample, I would not have been able to find this relatively complicated decision boundary. So from this small sample set, the best I could have done is maybe to find something simple like so. Okay, so what the Bayes classifier assumes in all of these formula, I always wrote the true probability, which is something that we don't normally have access to. So in this formula here and in this formula here, the true probabilities are needed. And we don't usually have them. And this is why there is this whole field of machine learning, because what we really have access to are just the training samples and not those true probabilities. Yeah, so here the same thing. This asked for the true probability that we don't really have access to. Okay, so summary. The Bayes classifier is the best possible classifier. Where best is in the sense of smallest expected loss. But best does not necessarily mean good. And even when it's not good, this best is usually unattainable for us, because except when I generate toy data myself, these true probabilities we don't have access to. And hence, there is this huge field of machine learning which tries to either estimate these probabilities directly or tries to estimate this posterior directly, to directly make a prediction. And this is written, what we discussed today is written in many books, but a nice one is this book by Bishop, Pattern Recognition and Machine Learning, where this thing is written up in chapter 1.5. And by the way, for last time, I also have some literature which I put in the document. It's a nice, for the double descent. As I said, the double descent hasn't really made it to the textbooks, but there is a nice overview paper which I thought I put in the document. I didn't. I will do so after this lesson. Okay, I will put in the reference for last time, the lecture on double descent. Good. So today, in the second hour, we looked at those two questions. Statistical decision theory answers them for us. And next time, on Thursday, we will look at various ways of estimating these quantities in real life. Remember Tristan's talk, could be interesting tomorrow. Thank you.